Molecular polarity. Molecular polarity is strongly related to the molecular geometry and the polarity of bonds. Let's begin with a quick review of the mechanics of a polar bond. Polar covalent bonds result when the electrons in a covalent bond are not shared equally. The strength of the resulting dipole is measured by the dipole moment, measured in debye, which is the product of the charge separated and the distance the charge is separated. Dipole moment is a vector quantity, which means that it has a direction as well as a magnitude. The direction of the dipole moment is always from the positive end of the dipole towards the negative end of the dipole. That is, it points toward the more electronegative element. The strength of the bond dipole moment is directly related to the difference in electronegativity between the two atoms. The larger the difference, the larger the dipole moment. However, just because the bonds in a molecule are polar does not mean that the molecule is polar. It is possible for the bond dipoles to cancel out if the geometry of the vectors is just right. If the bond dipoles cancel, the molecule will be nonpolar despite having polar bonds. One example of this is the molecule CO2, whose bond dipoles are exactly the same size but in opposite directions. By adding the individual bond dipoles, which are vectors, we can determine the overall dipole moment for the molecule. This is not always a simple thing to do, because the vectors and molecules are three-dimensional. We will not actually do any vector addition, which is more often done in physics. However, we will examine the different molecular geometries to see what we can learn about molecular polarity. When a molecule has only one bond and the bond is polar, the molecule is polar. If the molecule is tetrahedral with 4 equivalent bonds, it is nonpolar even if the bonds are polar. The same is true for any of the 5 types of domains if the domains are all equivalent bonds. For all 5 of the domain geometries, the sum of equal vectors in all the domains is 0. This is easy to see in the linear and octahedral geometries, and a little regular geometry or trigonometry can convince you that adding the 3 in the triangle results in 0. So the trigonal planar and trigonal bipyramidal molecular geometries are nonpolar. The hardest one to see is the tetrahedral geometry, but this can also be demonstrated mathematically. However, if all the domains are not bonds, then the molecule will be polar if the bonds are polar. It is also true that if the bonds are not all equivalent, then the molecule may be polar if any bonds are polar. So now let us look at the molecular geometries and see about the polarity. For the sake of simplicity, let's assume all of the bonds are the same and are polar. Remember, the bonds must be polar for the molecule to be polar, and the geometry must not allow the dipoles to cancel out. For the linear geometry, the dipoles are in opposite directions and will cancel out, so the molecule is nonpolar. For the trigonal planar domain geometry, the trigonal planar molecular geometry is nonpolar. But the bond dipoles do not cancel for the bent shape, so it is polar. For the tetrahedral domain geometry, the tetrahedral molecular geometry is nonpolar. But the trigonal pyramid, flat tetrahedron, is polar, and the bent geometry is also polar. For the trigonal bipyramid domain geometry, the trigonal bipyramid molecular geometry is nonpolar. The seesaw structure is polar, The two axial bond dipoles cancel, but not the two equatorial ones. And the T-shaped structure is also polar. However, the linear shape is nonpolar. For the octahedral domain geometry, the octahedral molecular geometry is nonpolar. But the square pyramid is polar, while the square planar is nonpolar. To summarize what we have learned, molecules are nonpolar if the bonds are nonpolar with any structure, or if the bonds are polar and all the domains are equivalent bonding domains, or the molecule is a linear or square planar structure. All other molecular structures are polar.